Hello everybody, welcome back to the stream. I think I fixed my audio issues as is usual with Windows audio issues. I have no idea what broke and I have no idea how I fixed it, but it should be fixed. Let's just have a last test here. All right, that looks good. Yeah, okay, that works. One thing I will have to do, so I got this video I'm going to play later. I scrolled that beforehand, but I need to redo that now.
That's the mains hum that you can sometimes plug in properly. Charge, balance, supply, or recording audio. You can hear it in the background sometimes, and then compare it to recording and also set them a challenge. Talk to one of the forensic. You'd have a perfect watermark to prove the time when anything was recorded. I talked to one of the forensic experts. You'd have a perfect watermark to prove the time when anything was recorded.
All right, that's where we're going to play the video later. Right. Should be ready to record the show now. Sorry, everybody. That's sometimes how it goes. With podcasting and streaming, everything breaks and you don't know why. Just to keep it interesting, I guess. Anyway, let's start the show. Let's get right into it. Let's talk about electrical network frequency analysis, which is pretty cool. Here we go. Let me see if I still know how that goes after all that crap. You're listening to The Private Citizen, defending your right to have something to hide, a podcast for critical thinkers. This is episode 123 for Wednesday, the 24th of August, 2022. Electrical Network Frequency Analysis. Hello everybody, my name is Fab. I'm coming to you live from the wonderful city of Düsseldorf in the west of Germany, in the Rhineland, and it's a balmy night, and we're gonna, well, when I record this, I don't know what time or season it is for you. It might be in Australia, it might be the height of winter right now, but anyway, we're gonna talk about electrical network frequency analysis today, obviously, which is a pretty cool new forensic technique. And I had that on the docket for months and months now. I wanted to do this episode. I always put it off because there was always something more pressing, and then I went on holiday. Now we're finally here. We're finally going to do this. I hope I'll have enough energy today. I'm preparing to run an athletics run on Saturday, so in a few days, and I'm recording this on Wednesday, obviously, and I've been training, and I've been running today. It was very hot, and I don't know, I think I've been training too much or something. I was very low on energy, and I ate something, and then it got better, and now the food coma is setting in. But I'll hope I get us through this show. It's an interesting topic, so it should be fine. In case you don't know what athletics is, it's kind of like it's like a survival run. It's like, I don't know, you run certain distance and there's mud and obstacles you got to climb over and shit like that. In my case, I'm going to run the 12-kilometer distance in a quarry in Wuppertal. So, it should prove interesting. But that's enough for my boring life. Let's talk about electrical network frequency analysis, or ENF analysis for short. Why are we talking about this? Well, it's interesting. It's I guess if you're interested in, I've talked about espionage before, and things like that, and privacy, of course. But it's network security. I'm interested in, and I hope you are too a little bit. At least the interesting parts of it. So if you're into any of that, or just cool technical things, then you find this interesting. Mostly because it's a technique to fingerprint audio files and maybe even video files, and it can be used to verify that when such files were recorded, but also to see if they've been edited in some cases. So that's pretty cool. It's already been used by the police in Germany and the UK. So it might be, and I'm a podcaster, of course. I'm ultra interested in this. So just to give you a very quick idea of what we're talking about, you're using main sum that is recorded on an audio recording to exactly pinpoint when this recording was when the actual recording time was. And to understand how that works, I'm gonna have to go into a few things. First of all, we need to understand what alternating current is. And I'm not an expert in this. Some people listening to the show might actually know a lot more about this topic than me. Bear with me. I'm just going to try to make this understandable, for anybody who might be listening to the show, might be new, or, not into electrical engineering. I'm not specifically into electrical engineering. I'm really not good with, I'm live recording this on Twitch. If you are actually watching the recording of this podcast on Twitch, you might have noticed that I pulled a random cable for the show, and I kind of fucked my audio interface over. So I'm not good with hardware in general, but I've dabbled a bit with ham radio and stuff like that, and that's when you get into stuff like alternating current and direct current, and I find it interesting. Not as interesting as software, but certainly interesting. So let's just give a very quick overview. This is something that, knowing this kind of stuff is something that just comes in handy in real life. Maybe you want to impress somebody at a party, or, like your father-in-law or whatever, might come in handy. So to understand how ENF analysis works, we need to first understand that there are two different forms of electricity that we mainly use. One is direct current and one is alternating current. And those are used in different kinds of, electronic circuits. Now, direct current is you in your life, you mostly know this from batteries. If you put batteries into a flashlight or a flashlight, I tend to mispronounce flashlight, and then people make fun of me. If you know that that kind of device, then you put batteries in it. That'll be direct current. And in a circuit that runs on direct current, basically the current runs, in the same. It basically only flows in one direction, from the negative to the positive part of the circuit. In an AC circuit, alternating current, it alternates. The current in the circuit alternates from positive to the negative. And I'm going to read some stuff, most of this on Wikipedia. There's actually some workable articles on this. So, just in case. Of course, if you go to the show notes at privatecitizen.press, you'll find links to all of this, and you can also what I'm reading now. You can read for yourself later in case you just zone out. But talking about alternating current. Many sources of electricity, most notably electromechanical generators, produce AC current with voltages that alternate in polarity, reversing between positive and negative over time. An alternator can also be used to purposely generate AC current. In an alternator, a loop of wire is spun rapidly inside of a magnetic field. This produces an electric current along the wire. As the wire spins and periodically enters a different magnetic polarity, the voltage and current alternate on the wire. This current can change direction periodically, and the voltage in an AC circuit also periodically reverses because the current changes direction. AC comes in several forms as long as the voltage and current are alternating. If an AC circuit is hooked up to an oscilloscope and its voltage is plotted over time, you are likely to see several waveforms such as sine, square, and triangle. Sine is the most common waveform, and the AC in most mains wired buildings have an oscillating voltage in the sine waveform. So that means if you plot, the current, you'll see like this, the sine wave. Now the question is, why are we doing this? Why is this useful? Like, why not have just electricity flow in one direction anywhere? Why not have, DC current, DC circuits everywhere? AC is most commonly found in mains wired buildings such as homes and offices. This is because generating and transporting an AC current across long distances is relatively easy. Actually, I lied. I think this isn't from Wikipedia. Yeah, this is too well written. It's from a site called Power and Beyond. I got some other stuff from Wikipedia later, but yeah. So anyway, just to give you the right source there, of course. This is because generating and transporting an AC current across long distances is relatively easy. At high voltages of over 110 kilovolts, less energy is lost in power transmission. At higher voltages, lower currents are produced, and lower currents generate less heat in the power line due to a lower level of resistance. This therefore means less energy lost as heat. AC currents can be converted to and from high voltages with ease by using transformers. With other words, we use this because we have a power plant somewhere, and then you need to get the power from the power plant to the consumer, right? And we use like these big power lines, and to get energy across them efficiently and try to lose as little power as possible, we want high voltages, and this is mostly easily achieved with AC. Whereas it would actually be very hard with DC current. Explaining this further, an effect of electromagnetism known as mutual induction, where two or more coils of wire are placed so that the changing magnetic field in one coil induces a voltage in the other, can be used to make a device called a transformer. So these are the big things, in these buildings attached to power lines. If there are two mutually inductive coils and one is energized with AC, you can also, they're also used in electronics, but these big transformers used for the power lines. If there are two mutually inductive coils and one is energized with AC, an AC voltage will be created in the other coil. The fundamental use of a transformer is stepping voltage up or down from the powered coil to the unpowered coil. This provides AC an advantage well above DC in the realm of power distribution because transmitting electrical power over long distances is a lot more efficient with higher stepped-up voltages and smaller stepped-down currents. Before reaching power outlets, voltage is stepped back down and current is stepped back up. This type of transformer technology has made long-range electric power distribution efficient and practical. Without transformers, it would be far too costly to construct power systems in their current long-distance form. And because mutual inductance relies on changing magnetic fields, transformers only work with AC. So basically, we use this ability to change the voltage and thus the current to transport power over long distances, which we do in high voltage, and then to not kill you if it's dangerous enough to put your, to put a fork or whatever into a power plug. We'll learn this as kids, right? When it's like 210 or 240 volts, that's bad enough. If it would be kilovolts, it'd be frying everything. So we use this, and this is why we use AC. But AC also is handy because, as this website also says, AC is also great for use in electric motors because motors and generators are the same device. The only difference between a generator and a motor is that a motor converts electrical energy into mechanical energy. These motors are used in all kinds of appliances like refrigerators, washing machines, and dishwashers. With other words, the thing they explained before, where you have a rotating coil inside magnet, basically an electromagnet, you can use that as a generator, i.e. you rotate the magnet with some kind of other energy, right? Let's say you have a power plant that produces hot steam. You can send the hot steam into a steam turbine, which turns, right? It turns a rod, and then this is very simplified, right? But you attach the rod to an electric generator. You turn the magnet in the coil inside of the magnetic field, and that creates electric power. And then you step up the voltage, whatever, transfer the power over power lines, and then in your home, you step down the voltage again, and then in your home you can have that same device work the opposite way, where you have power coming out of your socket going into a device where it will actually create a magnetic field, which will then turn a thing, right? Use this coil inside the magnet the other way around, where this time you're not putting mechanical power in to create electrical power. You now use the electrical power to create mechanical power, and that's your KitchenAid, right? The thing that turns your KitchenAid, or whatever. Of course, you can also have electric motors with DC. That's what your electric car uses. It's just generally, I think it's another kind of electric motor, but I'm not quite sure. But you can have that too, because your electric cars is powered by a battery. But if you want to know more about this, I put a link in the show notes, privatecitizen.press, to a Wikipedia article called "The War of the Currents," where it talks about Thomas Edison and George Westinghouse, where this is one of them. I think Edison was DC, right, and Westinghouse was AC, and they this goes into all the different upsides and downsides of AC and DC and all this kind of stuff, how dangerous it is, and all the uses and but the outcome of basically what you need to know for this episode is that the mains in your house are AC, right? And there might be devices connected to it that use DC, right? And there's I think are there also transformers? See, I'm not an expert on this kind of thing, but you can turn AC current into DC current. But the important thing to know is that we power all the stuff. My computer here, my audio interface, all of this is powered off a wall socket, and we have AC power coming out of that wall socket. And that brings us to the next point. Which is mains hum. Now, the problem is that this alternating current, that goes from positive to minus, to negative, several times a second, actually 50 or 60 times a second, depending on where you live, creates something, creates all different kinds of things. But one of the effects of this is something called mains hum. As Wikipedia says, mains hum is a sound associated with alternating current, which is twice the frequency of the mains electricity. The fundamental frequency of this sound is usually double that of a fundamental 50 or 60 hertz, that is 100 or 120 hertz, depending on the local power line frequency. Now, just a quick side note, this frequency, that the alternating current alternates in the power grid, is different in Europe, mostly between the US and Europe and the rest of the world. It's 60 hertz in the US, and in Europe, where I am, and large parts of the world, it's 50 hertz. Now, interestingly, Japan has both frequencies, which can cause all kinds of other problems that we don't want to get into. But this is something I actually just learned today. I didn't know this. I thought this was pretty funny. Now, if you ever recorded a podcast or tried to record yourself on audio or try to, record an instrument or even play an instrument, you might have heard main sum, which is a very characteristic sound. It sounds like this. So that's not your podcasting device malfunctioning. This is actually I'm playing this from Wikipedia. Now, if you ever I have a Telecaster, Fender Telecaster, which is a electric guitar that uses a single coil pickup, and if you plug that into an amplifier and crank the amplifier up, and you don't touch the guitar, you just have it hanging on your body, you will hear that sound. Because that pickup, being a magnetic coil, picks up this kind of hum from everywhere, basically. And it's very characteristic for that kind of pickup. That's why there's another kind of pickup which uses two coils that are in the circuit. They're kind of switched. They're canceling each other out. It's called a humbucker. It gives a different kind of sound. It's mostly associated with traditionally with guitars like the Gibson Les Paul, whereas Fender Stratocasters and Telecasters have these single coil pickups which sound brighter but have this main sum problem. And you've also I've had this in audio equipment all through my podcasting career. It happens a lot if you have it on your if you use built-in computer, like on a desktop computer, if you use that sound card to record stuff, you often have it on there. Sometimes, it's because on the motherboard, the components are too close to each other and it's kind of shitty. And it depends on, weirdly, what kind of power socket you plug your equipment in. So sometimes I've had it before where in your house, the wiring, you often you don't know how the wiring works. So you have like power plugs in the wall, and some of them might be on one wiring loop, and some of them might be on others. And so I've previously had this problem when I plug my computer into a power plug, and I plug my mixer into the same loop, and then my graphics card starts being used under load and draws a lot of power, I will get main sum on the mixer, which is called a ground loop, because both devices use the same ground. And then basically I pick up interference from my graphics card. So, weirdly, interestingly enough, main sum is not one thing. It doesn't have one source. There are many different kinds of main sum, and Wikipedia goes into some detail here, but the most common they describe as such: because of the presence of mains current in mains powered audio equipment, as well as ubiquitous AC electromagnetic fields from nearby appliances and wiring, 50-60 Hz electrical noise can get into audio systems and is heard as main sum from their speakers. Main sum may also be heard coming from powerful electric power grid equipment such as utility transformers, caused by mechanical vibrations induced by magnetostriction in the magnetic cores. On board, and this is an interesting side note, on board aircraft or spacecraft, the frequency heard is often higher pitched due to the use of 400 Hz AC power in these settings, because 400 Hz transformers are much smaller and lighter. So, and there's all different kinds of main sum. Wikipedia lists a few. Some of this you might have actually heard in real life, such as electric hum around transformers. So if you ever go near an electric switching station, right, where there's lots of power lines, sometimes they're close to power plants, or just at points between power lines. It's basically where the grid is regulated, where it's kind of, they do this stepping up of voltage and stepping down, kind of, they figure out how much power is used where on the grid, and then they kind of need to regulate this. And they have these buildings full of these large transformers. And if you go there, you can hear humming. As Wikipedia says, electric hum around transformers is caused by stray magnetic fields causing the enclosure and accessories to vibrate. Magnetostriction is the second source of vibration, in which the core ion changes shape minutely when exposed to magnetic fields. The intensity of the fields, and thus the hum intensity, is a function of the applied voltage. Because the magnetic flux density, this is great, this could be right out of Star Trek. Because the magnetic flux density is strongest twice every electrical cycle, so it cycles 50 or 60 times a second, 50, 60 hertz. The fundamental hum frequency will be twice the electrical frequency. Additional harmonics above 100, 120 hertz will be caused by the nonlinear behavior of most common magnetic materials. Around high voltage power lines, hum may be produced by corona discharge. And if you want to know what corona discharge is, links in the show notes. It looks pretty cool, but you'll hear that. My parents, across from where my parents live, there's power lines running along a field. As a kid, I would cycle home and cycle along the road, and there'd be the power lines, and I'd hear this like from the power lines. And it was specifically, I remember, loud when there was kind of like moisture in the air, like when the thunderstorm was approaching or something like this in the summer. It would be louder, which I thought was kind of creepy as a kid. As a kid, I thought it would be attracting thunderstorms, and I wasn't, I was a bit afraid of electricity and lightning and shit like that. Mostly because my grandma's house, when she was little, was struck by lightning, and she vividly told me that story several times, and it scared the shit out of me. Anyway, what else do we get? In the realm of sound reinforcement, as in public address systems and loudspeakers, electric hum is often caused by induction. This hum is generated by oscillating electric currents induced in sensitive, high gain, or high impedance audio circuitry by the alternating electromagnetic fields emanating from nearby mains powered devices like power transformers. Sometimes you get these cables pick this shit up. Like if you have very long cables and you have very sensitive audio equipment attached to it, you'll pick up electromagnetic fields because the cables, even though they're insulated, are basically antennas. The audible aspect of this electric hum is produced by amplifiers and loudspeakers. Like you amplify the signal and then you hear it. I.e., when you record a podcast, you get a mixer. The mixer will amplify the signal, sometimes picked up by your microphone, or the cables or whatever. Generally, you're picking up when you're home studio environment and you're not in a professional audio studio and everything's shielded and set up, professionally. Then generally you're picking up, the electromagnetic fields from your computer, from the other devices you're running in your room and shit like that. Sometimes it actually helps putting audio equipment in different power sockets. There's other ways. There's like these magnetic core things you can clamp around cables. That sometimes helps. There's actually devices that remove ground loops, which can be handy. Wikipedia continues. The other major source of hum in audio equipment is shared impedances. When a heavy current is flowing through a conductor, a ground trace that a small signal device is also connected to. All practical conductors have a finite, if small, resistance, and the small resistance present means that devices using different points on the conductor as a ground reference will be slightly different potentials. That is basically the scientific explanation of what I just said before. This hum is usually at the second harmonic of the power line frequency 100 or 120 hertz. Since the heavy ground currents are from AC or DC power supplies that rectify the mains waveform. And if you want to know more about this, there's a good Wikipedia article on ground loops. Interestingly, also in vacuum tube equipment, one potential source of hum is current leakage between the heaters and cathodes of the tubes. Another source is direct emission of electrons from the heater or magnetic fields produced by the heater. You get this in tube amplifiers, which I've got one over here that if you crank it up a lot, you don't even need to attach a guitar to it. It'll hum all by itself, which I guess was explained to me just now how that works. Tubes for critical applications may have the heater circuit powered by direct current to prevent the source of hum. Now, you can use this, I said in the beginning, to figure out when an audio signal was recorded. And we call that electrical network frequency analysis. So how does that work? So basically what you're doing, I'm going to read out, now Wikipedia has a good article on this as well, which I'm going to also link in the show notes. But basically what you're doing is power companies, what you need is a reference. So what happens in a power grid is this. A power grid, in the operation of a power grid, the power company needs to basically at all times balance the supply of power with the demand of power, right? They need to figure out how much power in the grid is used at any given moment and then supply the right amount of power. If you don't supply enough power, then you get brownouts or blackouts, right? There's not enough power for some devices. If you supply too much power, things are going to start exploding. I think those transformers are the first thing to usually, go up in sparks and explode. So you kind of need to balance this now, and they do this all the time, right? In the power, there's this scene in the Chevy Chase, in one of the Chevy Chase Christmas movies, with all these 100,000 imported Italian lights for his roof, right? And he plugs them in, and then the next shot is the guys in the power utility going, "Oh no, he's plugged the Christmas lights in. Power up the nuke plant," and then they power up an extra plant so they have enough power for his Christmas lights. That's basically what what happens. It's just over the top explanation, but they kind of balance the grid. Now, while they do that, they're invariably messing with this alternating current frequency, right? So let's say we're in the US, so all these devices expect 60 hertz alternating current, which means the utility needs to keep that at 60 hertz, more or less, so that things don't break. But it'll meander, right? It'll be 60.2 and 59.8. It'll go back and forth, and as long as that's not really bad, things usually don't break. Now, there was an instance I can remember a few years ago here in Europe where some grid supplier, I think in Eastern Europe, fucked this up a little bit, and things didn't really break except one thing. They're old alarm clocks, right? Which are powered off the mains. You plug them in the mains, and then you set the time, and they keep time by basically counting this alternating current, right? They go, okay, we're in Europe, it's 50 hertz, so it's 50 cycles per second, and they basically count those cycles, and that's how they keep time. And I think something happened, and was something with the power supply in Eastern Europe, and it kept reaching Germany and Western Europe, because these grids are all interconnected and shit, and so the frequency was lower than 50 hertz, which normal devices they can cope with, but these clocks slowed down, right? So your alarm clock would wake you up too late because it was slowing down because the mains frequency was off. So there are fluctuations in this mains frequency. So what you can do is you can plug a little device in the mains and then record, every second or every nanosecond or whatever. Well, that'll be quite, I think that'll be too fine grained. But every, I don't know, 10th of a second, whatever, you can record what the actual, probably doing it on the second, I don't know. You can record the mains frequency, right? You can go, okay, now it's 50, now it's 50.2, now it's 50.4, now it's 50 again. And you can basically collect that data. And researchers did. Now, these days, the power companies actually do that. And they have this data, and they give this data out, for example, to the police. And what you can then do is, if you get a recording, an audio recording that's long enough, and it has mains hum in it, that mains hum will shift, right, according to what the AC frequency was at the time. And because it meanders up and down, that creates like a pattern, right? And you can reconstruct this pattern. So you get a recording and you can see, okay, so I'm mapping so there's mains hum in the background, I'm isolating that, and then I'm mapping what it is, right? Like I'm mapping like the ups and downs, like the graph. And then I can compare that with an algorithm to my historical data of the power grid. Right? And then I can say, oh, I recognize this pattern. So this was recorded on, Wednesday, the 24th of August, at 21:18 hours, because this pattern was in the data at the time. And that's basically what ENF analysis is. Or as Wikipedia says, electrical network frequency analysis is an audio forensic technique for validating audio recordings by comparing frequency changes in background mains hum in the recording with long-term, high-precision historical records of mains frequency changes from a database. Now, this shit, right? If this fucking sounds like Star Trek. Sounds like science fiction, but people actually do this. And in effect, the mains hum signal is treated as if it were a time-dependent digital watermark that can help identify when the recording was created, detect edits in the recording, or disprove tampering of a recording. So if you edit that audio file, right, you have this waveform basically, or this meandering graph. From the mains hum, but then you'll have a break, for example. It shifts. You cut out 10 seconds, then your historical data will have 10 seconds of that waveform that's not in the recording, and can say, okay, somebody cut out 10 seconds there. It sounds like CSI bullshit, says Astro C in Twitch chat. Exactly, it does. Or like something Data would do. I watched an episode of Voyager last night where they have a spy on board, and they have to kind of figure out, the Neelix has become, it's Voyager, don't question. Neelix has become an investigative journalist, which I support, and then he figures out that there's the communications logs that have been tampered with, right? And this kind of thing would be something that like fucking, a Starfleet engineer would do to like a file to figure out if it was tampered with. But it's real. Historical records of mains frequency changes are kept on record, for example, by police in the German federal state of Bavaria since 2010 and the United Kingdom Metropolitan Police since 2005. So, I guess they already knew that in 2005. In the UK, police reportedly uses this technique in a fully automated process. Link to the register here in the story. It is important to point out that this technique has limitations. As Wikipedia says, according to a paper by, I think those guys are Dutch, Guybrechtse and Graz, I don't know. Link to the paper, or where, to get it, it's on Springer, so you can't really, psyop. I don't know what's wrong. It must be my allergies. Sorry. Better, sorry. You can, just look for the title. Anyway, according to a paper by Brechtze and Gerards, the NF technique, although powerful, has significant limitations caused by ambiguity based on fixed frequency offsets during recording and self-similarity within the mains frequency database, particularly for recordings shorter than 10 minutes. Yeah, because obviously there's not a big range this frequency fluctuates in, right? Because if it's if this discrepancy gets too big, then things start fucking up. So the power companies try to prevent that. Interestingly, there is also on this page, they also talk about using ENF on video signals. More recently, researchers demonstrated that indoor lights, such as fluorescent lights and incandescent bulbs, vary their light intensity in accordance with the voltage supplied, which in turn depends on the voltage supply frequency. As a result, the light intensity can carry the frequency fluctuation information to the visual sensor recordings in a similar way as the electromagnetic waves from the power transmission lines carry the ENF information to audio sensing mechanisms. Based on this result, researchers demonstrated that visual track from still video taken indoor light. Sorry, I'm trying to read this, but it's hard. My brain. I think I've worked too much today. I'm going to try this again. Based on this result, researchers demonstrated that visual track from still video taken in indoor lighting environments also contain ENF traces that can be extracted by estimating the frequency at which ENF will appear in video as low sampling frequency of video, 25 to 30 hertz, cause significant aliasing. So basically, this fluctuation of the AC frequency causes lights to flicker, which when you're sampling video at like 25 to 30 hertz or frames per second, right? Then you get aliasing in the video, and from the flickering of the light source. And then you can correlate that to the ENF record. That's some CSI shit. It was also demonstrated in the same research that the ENF signatures from the visual stream and the ENF signatures from the audio stream in a given video should match. As a result, the matching between the two signals can be used to determine if the audio and visual track were recorded together or superimposed later, which is pretty cool. So with this, you can kind of figure out when something was recorded, if you're lucky, if it was edited. That is pretty awesome. Now, to wind up this this report from me on how this works, I want to play you a bit of a video by Tom Scott. Now, Tom Scott is a YouTuber, a British YouTuber. He does great videos, basically explaining things. And he did a video in December of last year explaining what ENF is. Now, I just explained what ENF is, so we're going to skip that. But he basically went to some researchers who do this kind of thing, this forensic technique, and he shows how it's done in the real world. So let's listen to that a bit, because I thought this was fascinating. So this is Tom Scott. He's on YouTube. There's a link to this video and thus his channel in the show notes at privatecitizen.press. So I would, if you're interested in that kind of stuff, give him a follow or whatever, like and subscribe, whatever you do on YouTube, I guess. I appreciate this video, and let's listen how this works in the real world.
I talked to one of the forensic experts who works with it and also set them a challenge.
Historically, what's had to happen is we've had to record the grid frequency data ourselves by literally plugging a recording device into the mains. The National Grid have recently released their data, 7 years, recorded right at the source. It's fairly simple, actually, signal processing. You're looking to see if there is a component around 50 hertz or one of the harmonics. I would hesitate against advising anyone to present themselves to a court as a forensic expert, but this type of evidence has been used in court to date recordings. The longer recording you have, the better. As an absolute minimum, I think about a minute. If it's a noisy recording or if the ENF isn't particularly clear, then the longer recording you have, the better.
So, find the mains hum frequency in the footage and then write code to match it against the millions of possibilities in the National Grid logs. Does it work? Well, to find out, I asked some friends of mine who make videos to send me over some of their raw footage, straight out of the camera, unprocessed, unfiltered, and I asked the forensic team, can you timestamp it? First up, footage from Taha, one of the team behind educational channel Answer in Progress.
There's quite a strong component here, and you can see it's got a bit of a wobble. We use a signal processing algorithm to extract the peak, and we constrain that algorithm so that it can't suddenly jump up here. So even if there is a higher amplitude something up here, it will stick to this curve. Then compare. If we know that a recording was taken on a certain day, then we just need to give it a day's worth of National Grid data. If we're not sure when it was taken, we'll throw everything at it and it'll take a bit longer to process, but it's not prohibitive.
Spot on. Got it to the second. Although it's important to say that the team never said they were certain about the timing, only that they had a very high chance of being correct. And yes, they were. Next up, footage from Hannah Witten, sex and relationships educator.
There wasn't a component at around 50 hertz. So here we have the axis 49 hertz to 51 hertz, and we can see no apparent ENF trace. So I'm now going to change the axes up to around 100, and then we'll be able to see the harmonic component around 100 hertz. Because it's quite strong and seems to be behaving in a way that we'd expect the ENF to behave, we can be fairly confident that this is an ENF harmonic. What's interesting about this one is it sort of appears halfway through the recording. Maybe there's a little bit of something earlier on. So there's a possibility that maybe Hannah was moving around when she made this recording, getting closer or further away from mains powered equipment.
Maybe the mains hum was coming from something on a timer or a thermostat in the background that just switched off, but the timestamp was accurate. So the next test was Steve Mould from his science channel, and I thought that this one would be easy because he sent B-roll. He's not talking, and it's just ambient noise. And also, he is holding a fan that's plugged into the mains.
There's no strong component at all for ENF. So the next step would be to look at the other frequency regions to see if we can identify any harmonics. How loud the person is often doesn't have much of an effect. It's often environmental noise that would be lower to mask ENF. There is possibly something here, but because we haven't got a strong trace, it's sort of fading in and out, we wouldn't be confident to use this for an ENF analysis.
Sometimes it just doesn't work. As a last test, I sent over some of my old footage from when I was filming against green screen in my tiny flat last year. I was sneaky though, and I hid an edit in there.
What could happen with an edit is you'll have a sudden jump in the ENF frequency. In that case, it's quite likely to be an edit. It's possible that the ENF trace will just sort of stop. The reason for that could be because it's got an edit in, which in this case we believe it has. But it could also be because you walked away from the source of the ENF energy.
Like any forensic analysis, this isn't some magic tool that always works. Compression can stop it working. You need minutes of uninterrupted audio to have enough confidence in the result, and sometimes there might be no background mains hum at all. But I love this because it's an accident of technology that's created a tool that would sound like science fiction 20 years ago.
Yeah, and I think he's quite right on that. It sounded science fiction when I first read about it. So pretty cool. Yeah, you can probably do that on my podcast, although I guess I don't know what the MP3 compression does to them, but you'd certainly have enough material. I'm with my incredibly unprofessional audio setup here. I'm bound to have a lot of hum. I kind of try to filter it out. I run some EQ over this podcast. When I master it, that should cut hum out, and it should cut that hum out, but I don't know if that actually works. So if anybody wants to actually try this, and it'll be academic because I'm streaming this right on Twitch, so you know exactly when it was recorded and that there were no edits, or at least you get a version with no edits. Sometimes there are tiny edits, which I usually just do for your convenience. But if somebody wants to try this kind of thing, I think I get a kick out of it. As Lucy in Twitch said, let's find out when this current podcast was recorded. Wait a minute. I'm there. I'm right there. Anyway, I thought this was a neat technique. I'm not telling you about it because, oh my God, we all need to be scared. Because it's some huge like privacy issue, of course. But just keep that in mind. This is certainly something that this is kind of like a reality winner situation. You could see this happening. You could see this tripping up a whistleblower, maybe, who's trying to kind of hide when they recorded something or where they recorded it, alone something being at 60 hertz, some hum in the background might tell you that it was recorded in the US or certain parts of Japan, I guess. Just pretty fascinating stuff I wanted to share with you. I hope you find it as fascinating as I have. And with that, we're leaving the today's topic of the show. And let's talk a bit about some of your feedback. First of all, I had many messages from people who wrote me after the previous episode, who basically said that they're happy that I'm back at my desk and working, and continue to produce this podcast. So one of the people who told me this was Necros on the forum, and I just wanted to tell everybody what I responded to him on this. Just thank you for telling me that once in a while. That's really helpful. Certainly I get a lot of negative criticism a lot of the time, which comes with the territory, but sometimes really nice people telling me that they appreciate what I do. It just kind of gives me the energy to continue with this stuff. And I also had a nice email from Johan Sonen, who teaches at MIT, who I covered. So he gave a talk at, was it FOSDEM? I think it was FOSDEM. I covered this in episode 57. Let me just, do I have the right? Yeah, it was at FOSDEM. I actually wrote about this talk for Heise Online as well. He was talking about medical data, owning your own medical data. And I guess he stumbled across my episode. So he wrote me a nice email saying that he discovered the episode and sent me some nice words, which I appreciated as well. But also he is basically part of an effort called opensourcehealthcare.org, which I found really interesting. And this is something I want to devote more time on, talk about in another episode. Maybe I can get him on for an interview. Basically, this is, continuing on the same note as that. In his talk, he talked about creating a system where you own your own health data, which I think is crucial. It creates all kinds of problems. But, there are all kinds of problems. Currently, I think it depends largely on where you are. In Germany, for a long time, we just had physical records, and they resided with your doctor. So I have a problem. I go to my GP, and they look at me and then do a diagnosis, and then they have those files, right? And a file on me, and with the diagnosis and what drugs I got. And they might refer me to a specialist, and then I go to the specialist, and then the specialist gets sent that file. But that file is always at some doctor. And if I go to another doctor, they need to get that file sent. We're moving this to digital records now, but it's still kind of the same thing. They need to keep sending on those records. This sometimes creates problems. My wife, who does research in a hospital, recently told me the story how this is a huge problem. How they get a guy in with a heart attack. I mean, I'm laughing. It's not funny, but the situation is almost comical, right? They get a guy in with a heart attack, and then he tells him he's kind of a history of heart disease, and then they need to, they kind of want to help him, and they need to know what drugs he's gotten in the past, what has been diagnosed. So they need to get into contact with let's say he's been in another hospital with a heart attack before, or some other heart disease. They need to get in contact with that hospital, and they spend significant time calling up that hospital and getting the file like sometimes in the middle of the night, and it creates all kinds of problems. So, the obvious answer by most of these, not technically minded people who are just doctors who want to help you is like, we need some central database for this shit. Now, if you're listening to this podcast, you've listened to me, talk a lot about IT security and stuff, and you immediately have a red light in your head probably going off like, red alert. Because, that creates all kinds of different problems. Now, Johan was talking about how we could create such a system either. It could be distributed. It could be central, could be on a blockchain, of course, but like in a way that's secure. And there's certainly solutions for that. But like open source healthcare even goes further. It kind of, as far as I understand this idea, it kind of wants to open up all of healthcare, like how drugs are created, how they are tested, how they are researched. Like this is all the realm of big companies right now that make a lot of money, and it's not necessarily the best for patients, right? And if you know how medical research is done, this. Medical researchers know this. Of course, they have to arrange themselves with the system, but I think it's good that there are some people who want to change that. I don't know how realistic that is. It's kind of modeled. They kind of model this idea after open source in software, which was remarkably successful in considering that it's the same kind of like David versus Goliath idea, where it's just a few scrappy rebels against the big, industry juggernauts. Now the pharma industry has much bigger juggernauts, so it's gonna be a harder fight. But I understand. I feel like pretty much anybody after the recent pandemic should understand a lot of these problems that we have in healthcare systems, in all healthcare systems. I'm not even like on this level. There's no difference between the German, the UK, the Australian, or even the American healthcare system. They all have the same problems. We might have social healthcare in Germany. We still have the problem that the companies are in control of how drugs are created, how many treatments are, how new treatments are developed, how they're tested, how vaccines are created, how they are tested, all this kind of stuff. I find this very interesting. This is another thing I put on my list of topics. Actually, I say that, and I wanted to, and I haven't. So I'm going to do that. I'm going to do that live on the show. I have a page here. I'm going to put that on there. opensourcehealthcare.org. Open source. So I'm not cutting this out. So no, don't need to use ENF to figure out if there was an edit here. Where was that? Open source. Sorry, open source health care. I got a cough again. Sorry, open source healthcare.org. Yeah, this is going to be a topic I definitely want to talk about. And maybe I can get Johan on and interview him about this and their goals and these kinds of initiatives, because I think it's very important, especially with everybody going on about the healthcare system is so important, and we need to protect people and the evil virus, and for all of that talk I've been ranting about this a lot on the show. For all of that talk, there's been precious little change in our healthcare systems over the last 2-3 years. Even though we just lived through the biggest, social situation, that you'd think would kind of initiate such change, but basically nothing has changed. So yeah, I found that a bit disappointing. But anyway, let's wrap up the show, because before I just rant endlessly, and let's talk about how you can help me do more of these episodes, maybe. in essence, this show is produced after something called the Value for Value model, which was pioneered by the No Agenda Show, Adam Curry, John C. Dvorak, which basically means you get the show for free. But if everybody gets it for free, then I don't make any money. I'm scraping by as a freelance journalist anyway. I'm making myself incredibly unliked by the general public, speaking truth to power. This week, the the House of the Dragon show, which I watched, and yeah, it's not that good. Anyway, yeah, you need to help me out if you want to keep the show on the air. A lot of people are already doing that. You can become a patron on Patreon. Links in the show notes, privatecitizen.press. There's a PayPal email address if you prefer that, if you don't want a recurring payment. And, any way you can help is appreciated. And you don't even have to, support the show monetarily. You can also write me feedback. There's a link to, contact link at the top. There's a link in the feedback section. If you want to give me constructive criticism. I've been talking about electricity too much this show. Constructive criticism, ideas for future episodes. If you just want to rant at me or just need somebody to talk, yeah, please contact me. I appreciate that. I like to know who I'm talking to when I do these shows. So, yeah. And with that, let's list all the people who've, lots of people have written to me and given me feedback and helped out that way. And all producers, as for the, as the Value for Value model stipulates. But they're also the producers who kind of help me pay the bills. And I'd reserve special thanks for them. So thanks to Gal Taryn, Rodane the Insane, Steve Hose, Butterbeans, Michael Small, 1I11G, Jonathan M. Hetai, Michael Mullen Jensen, Dave, Jaroslav Lichtblau, Jackie Plage, Sandman616, IKN, Bennett, Piata, Vlad, Rizal, Avis, Joe Poser, Dirk Didi, Kai Sears, Fadi Mansour, David Potter, Mika, Cam, Mr. Amish, RJ Tracy, Captain Eckhead, Rick Bragg, Ricky M, Barry Williams, Jonathan, Robert Forster, Astral C, Crunkle, Superuser, D, Florian Pigorsch, and Eric Lillay. I also thank my Twitch subscribers, Mike the Dane, P. Keemer, Bacon the Pork, Redeemer F, L. Terrestrius, Jim, Galtaran, Jonathan Haynes, 4747, and Indie Gameiacs. Thanks to all of you. Also thanks to Bytemark at bytemark.co.uk, great British cloud hosting company who have been providing the servers this show resides on and the bandwidth that you use to get the files ever since this podcast has started. So I thank them very much for that. And with that, it's Fab Out. I'm out of here. And I am gonna play you out. Of course, the theme tune for this podcast called Acoustic Roots by Ro Kabzali. But, I have the habit of playing you out with a different song every episode. I've started this with episode 51. And for this episode, I've picked a song called The Silver Lining by Hara Noda, who does some amazing jazz. You can find him on Epidemic Sound, or her. You can find them on Epidemic Sound. So I'll see you next week, hopefully next Wednesday, with another scheduled release with some more stuff. I don't know what I'm going to talk about then. I hope you found this episode interesting. If you want me to talk more about stuff like this, let me know. Details on privatecitizen.press. See you soon. Aim to misbehave. Isn't that a lovely song? I love how that fades out. It seems like I was able to record a podcast. It's pretty cool after all those technical issues. Thanks for bearing with me, everybody. I'm now gonna go off stream and finish this podcast and get it out and I don't know, collapse, I guess. I'm a bit tired. Must have been that run. Anyway, I'm going to radio over to Amazonian, who's playing Magic the Gathering. He's been playing for 7 hours, apparently. Yeah, that's it for me. Hindenburg strikes again. It wasn't Hindenburg. It wasn't the Hindenburg burning down in flames. It was fucking Windows. It's Windows hiding the audio interface from everything. For some reason, OBS could still use it. I don't understand. I don't understand. At this point, I've been doing this for like 15, 16 years. I'm like, it's basically magic. It's like I just do some hand wavy things. I'll burn a chicken in the backyard and then I'll pray to some gods and then I hope it works. Yeah. Anyway, let's rate Amazonian. Thanks for watching. See you soon, everybody. I appreciate you bearing with me. Thank you.